So good afternoon and welcome back. So in the last class we did the floating point IEEE precision representation and how to recover the decimal numbers. And we just started off with the complements also, though we have covered the complements portion slightly earlier. We will slightly repeat, but with a more professional way. We will give you the steps on how to solve the complement numbers. So to start with, what is the general procedure to do R's complement? Whenever I say R, it means that R is nothing but your base, right? So R here represents your base. This can be any number starting from 0 to 9. Okay. So if you have a base of 5, then R represents 5, and the complements that are possible are 5 complement is possible and R minus 1, which is 4 complement, is possible. I have repeated this multiple number of times. In case, so as a general rule, what is the procedure to do subtraction using R's complement? I am giving you a general method. If we say here as far as we are concerned, we are more interested in the two types of complement where our base is either binary or it is in decimals. We are interested only in these two bases, at least currently, because why tens? Because this is what we interpret as humans. That is why we are interested in tens complement. Why twos? Because this is what computers will understand as far as the twos complements are concerned. So to start with, how do you perform a subtraction using R's complement? If, say, for example, you want to do m minus n as a subtraction, m and n are two different digits. So first, what you need to do is perform this subtraction using complement form. So this subtraction you are going to perform as m plus minus n. So what you need to do is you need to convert this minus n to the complement form. So first step is take R's complement of this number. If it is a tens complement, then takes tens complement of this number. If it is a twos complement, take twos complement of this minus n. Then what you do is add m. You will add m to it. If you get a carry here, then discard the carry. If there is no carry, then take again the complement of that particular number and then place a negative sign before it, right? So this third step will happen only when your m is greater than n. Okay. Your fourth step will happen only when your m is less than n. Okay. Now let's take a quick example. If you want to perform this particular subtraction using, obviously these are decimal values, so you can perform only tens complement. 7, so you will not have a carry getting generated here. Why? Because m is greater than n. So m here is 72532, n here is 3250. First step is step 1, as mentioned here. Take the R's complement of this number n. What is the R's complement? R here is 10. So 10's complement of 3250 is either you can take 9's complement and add 1, or you can subtract it from 10,000. Whichever is easy, you can do it. So let us take 9's complement and then add 1 to it. 9's complement of 3250 is, just keep subtracting from 9999. You will get 6749, add 1 to it. 6750 is the 10's complement of 3250. Now, if you want, you can also add 5 digits also, it doesn't matter. Okay, so if you take 5 digits, then you will be subtracting from 99999 minus 3250. So when you subtract, you will have 9 added to 6749. When you add it, it is 96750. Why it is recommended that you use 5 digits here is instead of 4 digits here, because you are subtracting from 5-digit number. This 3250, though this is a 4-digit number, you are going to subtract it from 5-digit number. Obviously, as a decimal subtraction, this is a conventional method. Minus 3250 is a conventional method. Instead, we are forgetting that we are having a 0 here. Javier, could you please mute? Thanks. Okay. Okay. So we are forgetting that we are having a 0 here. So if you remember that you are having a 0 here, then obviously you will subtract from 5 nines 0 through 250, then you will do the 5-digit subtraction. So since it has been we have been acquainted with forgetting the 0 and then doing it with four digits, we should not do it with 4 digits. Whatever is the maximum digits that you are having in this subtraction, use that particular number of digits when you subtract this 9's complement form. So instead of performing this subtraction, perform this particular subtraction using 5 digits, so that will be easier and you will result in a correct form. Now what you should do, you should add the two numbers m and n. So m value is 72532 and the complement form is 96750. So when you add 96750, so 2 plus 0 is 2, 3 plus 5 is 8, 5 plus 7 is 2, remainder 1, 6 plus 2 8, 9, and here 9 plus 7 is 16 and carry 1. I have already said that m is greater, whenever m is greater than 1, n, you will get a carry and you can discard that particular carry. So discard this particular carry and carry the positive sign to it. So what is the answer here is, answer here is going to be 69282 is the answer when you subtract 72532 with 3250. Any doubt here? Okay. Now let us take a larger number subtracted from a smaller number. Obviously, this will result in, after adding 2, you will have a carry, you will not have a carry, and then you have to take further complement here because m is less than n here. So let us see what happens. First, you need to take the tens complement of this number. So m here is 3250. Please note here, with my previous experience in the problem, I have added 0 to it. So m is 03250 and n is 72532. The tens complement of the number is subtracting the 5-digit number from 5 nines, 99999 minus 72532, and then adding 1 to it will become a tens complement number. The resultant will be, so when I subtract 5 nines from 72532, so this is going to be 76472. So 27467, 1 added to it, 27468. Now I will add it with my m value. M is nothing but m plus n bar. Bar represents the complemented value of n. So m plus n bar is 03250 plus 27468. Please note here there is no carry here. If there is no carry, then you have to further take the tens complement of the answer. So since there is no carry, now what is the tens complement of this number? I will take 9's complement and add 1 to it. So 99999 minus 30718. So this is going to be 18296 and I add 1 to it. So the answer is 69282. So the answer is 69282 and I will put minus sign to it because I am not having a carry here. So put minus sign. So the answer is minus 69282. This is for using tens complement, that is R's tens complement. In case if your R value is 2, which is a binary value, then also the rule is the same. Let us quickly do that also. We have two binary numbers, X and Y. First, let us perform X minus Y and then let us perform Y minus X. So first we need to convert this number. We are performing X minus Y. Okay. So this is your X value. This is your Y value. We have to first take the 2's complement of this. You already know a shortcut method to perform the 2's complement. What is that? You travel from right to left. When you encounter 1, you copy till that and then complement everything. So if I complement, it will be 0 and then 4 zeros becomes 4 ones and then 1 becomes 0. So this is the 2's complement of this number. I add this number with 1 0 1 0 1 0 0. I have to add these two things. I will get a carry definitely. If I get a carry, I will ignore the carry and I will use the rest of the magnitudes as it is as my answer. So obviously here we do not know where, obviously here you can see that X is greater than Y. So here when you add here 1 0 1 0 1 0 0 is the X value and the complemented form is this one 0 4 times 1 0 4 times 1 and 0 1 is the complemented value. So when you add, you will see that there is a carry that is getting generated. We discard this carry and the rest of the value we use it as the final answer. So this is what is the resultant is 001 0001. Now let us do the reverse, y minus x. Please note here that now y is smaller and x is greater. The result will be negative. So here in this particular case, you will not get a carry. When you don't get a carry, you will further take the 2's complement of the answer after adding with m. So here let us see. You want to perform y minus x. We will do this by adding y plus the complement of x, y plus x bar. If x is this one, 1 0 1 0 1 0 0, what is x bar? That is the 2's complement directly. I copy till this 1 0 as it is and then I complement everything. 0 becomes 1, 1 becomes 0, 0 becomes 1 and 1 becomes 0. Or the other way is take 1's complement and then add 1, both will be the same. These both will be the same. So taking 1's complement here becomes 0 1 0 1 0 1 1, right? 0 1 0 1 0 1 1. You add 1 to it, becomes 2's complement. Both are same. Now you add y plus x bar, there will be no carry. So 1 plus 0 is 1, 1 plus 0 1, 1, 0, 1 and 1. There is no carry. If there is no carry, you will again take the complement of this one. That is the 2's complement of this. What is the 2's complement of this? Directly you can write. Travel from right to left. You copy till you come across 1. So I have come across 1. In my LSB itself, I copied till 1. Rest all it is complement 0, 0, 0 and then 1, 0, 0. Right? So 0, 0, 1, 0, 0, 1 and put a negative sign to it. So minus 0, 0, 1, 0, 0, 0, 1 is the answer. This is how you perform subtraction using R's complement. Similarly, R minus 1's complement. Now, R minus 1's means since we are interested in decimals and binary, let us focus towards what is for decimal, R is 10, 10 minus 1 is 9's complement and for binary 2 minus 1 is 1, so 1's complement. Here also the rule is the same, but a slight difference. What is that is, you will take first R minus 1's complement, you will add it with m. If there is a carry, then you will add that particular one carry to your LSB, the left rightmost digit. Even after decimals, you come across decimals also, you have to add it with 1 to the rightmost bit. If there is no carry, then you have to again take the r minus 1's complement of that particular number and put a negative sign in front of it. Okay, what is the only difference between r's complement subtraction and r minus 1's complement subtraction? It lies only in the third step. In the third step, if you have a carry in r's complement, you will discard it. If you have an r's carry in r minus 1's complement, you will add that particular one to your LSB. So let us follow that. I am just slightly moving faster. I have taken the same example. 72532 minus 03250. From our previous experience, we are not subtracting it from just 4 nines, but we are subtracting it from 5 nines here because this is a 5-digit number. So subtracting from 5 nines minus 03250, 96749. Now subtracting it, I am getting it. Now I will add with m. So this is my step 2. Step 3, I am seeing a carry here. If it is r's complement, I will ignore this carry, but here I am adding the carry to my LSB bit. So if I add this to my LSB bit, it is 69282. Now let us perform n minus m. So this particular step is your step 3 because m is greater than n. Now in this example, m is less than n, so you will not come across step 3. You will come directly to step 4, meaning your answer will be negative. You will not have any carry. You will take further r minus 1's complement. In this case, you will take further once more 9's complement of that answer when you add. So what is the complement of m here? It is 5 times 9 minus 72532, 27467. You will add it with n, so you are not getting a carry here. If you don't get a carry, you will once more take the 9's complement of this number. So the 9's complement of this number further taken will be 69282, and you will add minus to it. That is what is your n minus m subtraction using r minus 1's complement. Any doubt? Similarly, let's perform the r minus 1's complement for binary numbers. So x minus y. So taking the complement of y becomes, I am taking not the 2's complement, since this is r minus 1's complement. In binary, it is 2 minus 1 is 1's complement. I have to take 1's complement only and not 2's complement. 1's complement is fairly simple. You just invert all the bits of y. So, so y bar becomes 0 4 times 1 00. And then you add x to it, 1 0 1 0 1 00. I am getting a carry. Obviously, I will get a carry, right? If I get a carry, I will add that 1 to my leftmost bit. So this will be my answer. Similarly, if I do in this particular case, I will not get a carry and I will take further complement of my number. So I am going to perform y minus x, where x is this one. X bar will be, the complement of x will be just a complement of this 0 1 0 1 0 1 1, the same number. Now you add with y. So y is 1 4 times 0 1 1 and x bar is this one 0 1 0 1 0 1 1. When you add this, you will have, you are not getting any carry here. There is no carry here. So if you don't get a carry, you will take further complement of this one. So what is the further complement of this number? It is 0, 1 becomes 0, 1 becomes 0, 0 becomes 1, and 1 1 1 becomes 0 0 0, and this 0 becomes 1, right? So this is how you perform subtraction. So we have seen how to perform addition, how to perform subtraction. Normally subtraction is performed by complemented form. Now let us do the multiplication. Multiplication, again, it's fairly simple, like your decimal multiplication only. So decimal multiplication, it is 1 into 1 is 1, 1 into 0 is 0, 1 into 0 is 0, and 0 into 0 is 1. So taking an example here, 10001. So it is like similar to a normal multiplication. This 1 gets multiplied with my multiplicand 1001, 1001. 0 multiplied by anything is 0. 1 multiplied by this same number. Again 1 multiplied by the same number. Now I need to add all these column wise. So it is 1, 0, 1, 0, and with a carry 1, 1, and 1. So this is how you perform multiplication. Fairly simple, since it is prerogative to cover all the arithmetic operations, we are doing it. Again, binary division is also similar to how you perform the decimal divisions. In case you want to divide 110 by 11, then you follow the same process. 1 times 1. So when you subtract, this is going to be 0. You drop down 0. You add 0 to it. So this is the answer. Normally, computer will not perform divisions like this. They will not perform like this. Division is performed by shifting operation. Okay, system, your computers, they will perform the division by successive shifting of bits. So we will see this later, but at least for time being, you can also perform your binary division similar to normal decimal divisions. Next, normally Verilog program is covered, but if it is a physical class, we will do it. Otherwise, we will not force you to do it. And these Verilog programs are important only for electrical students and not for that is EEE or ECE students, and not for computer science. Yeah. So hence we are skipping the programming part. Now coming to, there are different codes that we have in binary, in number systems normally. If you classify the codes, we have classified it into numeric codes and alphanumeric codes. Your alphanumeric codes are further classified into ASCII codes, EBCDIC codes, and Hollerith codes. We will come back to ASCII codes. You all very well know, right? Now this numeric code, they are classified into many types. We will not be handling this alphanumeric code, that what you see in your keyboards, the machine language codes, they are all alphanumeric codes. You will have alphabets as well as the numbers in these kind of codes. Now in numeric codes, which we are interested in, they are classified into these 7 types: weighted codes, non-weighted codes, self-complementing codes, sequential codes, error correcting and detecting codes, reflective codes, and cyclic codes. Now further, this weighted codes are classified as binary and BCD codes. What is BCD is binary coded decimal codes. Binary coded decimal codes. And non-weighted codes, they are classified into XS3 codes, gray codes, and 5-bit BCD codes. Out of this, I'm just going to highlight only few codes here, which is of interest to us, and what are the codes that we will be doing. Okay, so the codes that are interested to us are all these ones. That is, we will be working on weighted codes, non-weighted codes, self-complementing codes, sequential codes, error correcting codes, reflective codes, and cyclic codes. Weighted codes, we will be working, obviously binary codes is what is of our interest to us, and we will be working on BCD codes. In BCD codes, we will just work on 8421 only. For example, we will look at 2421 codes, and maybe for just for an example sake, we will look at 84 -2 -1 code also. In addition to that, what are the other codes that are of interest to us are the non-weighted codes. In non-weighted codes, we are more interested in XS3 codes and gray codes. Please note that certain codes are common to multiple classifications. Say if you look at an example here, this 8421, this is a weighted BCD code. This 8421 is also belongs to the sequential codes. So likewise, there may be an overlapping of these codes that are available. Another example that you can see here is this XS3 code and gray codes. These are non-weighted codes. These are non-weighted codes. They are not only non-weighted, they are also reflective codes. They are also cyclic codes. Okay. So, and this XS3, if you look, they are not only non-weighted codes, they are self-complementing codes also. So what is that you need to learn? So many confusions, so many different types of codes. All you need to understand is you need to look at this particular block. You must know the basic definition of what do you mean by weighted codes, what do you mean by non-weighted codes, what do you mean by self-complementing codes, what are sequential, error correcting, reflective and cyclic codes. You must know the basic definition and understanding of these codes first. Now, as I mentioned, for sake of example, we will look some of these things that are highlighted, say 84 minus 2 minus 1, 2421, and then there are called as biquinary codes. And I'll just look at the further classification, then we will go back. Some codes of self-complementing codes. What are self-complementing codes are? The 2421, that is already a weighted BCD code, it is a self-complementing code. Similarly, 5211, which is a weighted BCD code, it is also a self-complementing code. A non-weighted code, which is an XS3 code, is also a self-complementing code. Similarly, a weighted BCD code 8421 is also a sequential code 8421. 4. Here the 4 corresponds to a sequential code. Another example of a sequential code is XS3, which is also a self-complementing code. Okay. Now, error correcting codes. There are two kinds of error correcting codes: parity codes and Hamming bit codes. Right? There is one separate chapter, separate subject in electrical engineering called as error correcting and error detection. The course name itself is error correcting and error detection, which is very, very useful for communication engineers. Okay. So one course itself is there on this particular topic. Now, what is that we need to summarize here is there are straight binary numbers and obviously the natural binary numbers like 0, 1, 2, 3. Based on that, you have the alphanumeric codes. Then you have, in general, you have BCD codes. There are multiple classifications to it. Let us not bother about that. And XS3 code, normally this XS3, it is written this way also, X, S, and 3. And then you have gray codes, alphanumeric codes we have already seen, and error codes. Right. So to start with, let us cover few codes here which is of interest to us and which is of interest to the computers. To start with, let us start what is a binary number or binary code is. Binary number, you all know that they are represented with, each binary number is represented with a circuit. If you are writing 0 or if you are storing a 0 here, they have an electronic circuit to represent 0 and 1. So 0 is represented with some electronic circuit, 1 is represented with some electronic circuit, and 0 is represented with some electronic circuit. Normally this electronic circuit will be like a crosswire. It will be like a crosswire. These are all few. Say for example, these are all these row lines or some power lines or say input lines you can consider. These column lines are also some power lines. So if you want to store 0 or 1, normally what happens is there will be a switch like this. If the switch is connected, then it represents that this is 1. if this is connected. If the switch is not connected and if it is open, normally this is represented as 0. And what is this particular switch? If I zoom and enlarge this particular switch, okay, I cannot draw. If I zoom and enlarge this particular switch, then this circuitry is nothing but a transistor circuitry. You will have a transistor to it. So that is the reason it has been mentioned here that if you have n binary bits, then it means that there are n circuit elements there, right? If I'm having 0 here, it means that there is a transistor behind that particular 0 where that particular transistor is open. If I have 1 here, I am having a transistor behind that where that particular transistor is conducting. That is what it means. So here, coming to the values of these particular n bits, normally the number of distinct combinations of a binary code is represented by 2 power n distinct combinations. If I say that I am going to operate in 3 bits, then the number of binary bits that are possible are 2 power 3, which is 8 bits are possible. If I say n number of bits, I am going to operate in n bits, then it means that 2 power n number of bit combinations are possible. So what are the two values that can be represented in binary bits? You already know. We call it as 0 or 1, it is off or on, or it is true or false. So if I have 2 bits, then the two possible values that are available are 0, 0, 0, 1, 1, 0, 1, 1. When I say that I have a 3-bit configuration or 3-bit architecture, 3-bit combinations that are possible are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1. So 8 different values are possible. If I have n bits, then 2 power n values. For example, 4 bits, total 14 values are possible. Okay, here also it is 2 power 3 is 8. That is how 8 different possible combinations are present here. So n bits, normally they will take unsigned decimal values only, ranging from 0 to 2 power n minus 1. Why this minus 1? Because we are including 0 here. So out of the many binary codes that are available, that are listed in this particular table, we are going to focus towards a BCD code. Having studied what is a binary code is, now let us focus on BCD code. What is BCD? Why we are giving so much emphasis on BCD is, as humans, we can read the decimal values from 0 to 9, right? So normally when people started working on the binary systems, then the one thing that was easily for them to interpret between decimal and binary was this BCD codes only. So as the name itself implies, you can see here that binary coded decimal, meaning we read from the reverse, a decimal number here is being coded with a binary value. That is what we mean. So BCD code provided an excellent interface between the decimal system and the binary system. So why they provided an excellent interface is, say how many decimal digits we have? We have 10 decimal digits, right? Including zeros. So if you have 10 decimal digits, then if you want to represent in binary, what must be the possible number of binary bits that needs to be coded? You must at least have a minimum of 4 bits to code this 10 decimal digits, right? So which means that, but 4 bits in binary corresponds to 16 possible decimal values. So, but how many decimal symbols or decimal digits we have? We have only 10 decimal digits, but we have 16 different possible combinations. So which means that 16 minus 10, there are 6 unused or unassigned codes are available in BCD code. This BCD code, either as in this particular classification here, there are different classifications of BCD codes also. 8421, 2421, 3321, 4221, 4211. What are these? These are the weight positions of the binary bits. So I'll tell you what is this 8421 is. Now BCD code or 8421, as I said here, if you want to represent 10 decimal digits, then you need 4-bit combinations of binary values. So we are having 4-bit binary combinations of binary values. All these decimal values, that is starting from 0 to 9, can be correspondingly coded to binary values. Why did I say the 8421 code is? 8421 is nothing but 2 power 0, 2 power 1, 2 power 2 and 2 power 4. 2 power 0 corresponds to 1, 2, 4, sorry, 2 power 3, 8. So that is how you got this 8421. That is the positional weights. So 1 corresponds to 001, 2 corresponds to 0010. Please note here that these are the positional weights. I should have written it here: 8th position, 4th position, 2th position and 1th position. So you want to get 3, I can have a combination of 2 and 1. So I have 1 and 1 here. If I want 4, I already have a 4 here, so it is 4. If I want 5, 4 plus 1, 5. So I have 1 and 1, 0, 1. So likewise, I can code all the 9 decimal values. But more importantly, what about the other codes? I have 16 possible combinations. So the other possible combinations, they are considered as invalid codes in BCD codes. What are invalid codes? See, after 1001, what are the possible combinations? I can have 1010, 1011. Don't say that this is A, B, C, D. Those are all in hexadecimals, not in decimals. So hexadecimal number system is different. We are looking at decimal number system and binary number system interfacing. So the 1010 corresponds to nothing in decimal. 1011, 1100, 1101, 1110 and 1111, they are all nothing in decimal, meaning they are all invalid codes. So why this BCD? We are calling them as a weighted code. Here you see here that the main classification itself is a weighted code here, right? These are weighted codes. Why BCD is called a weighted code? Because each binary bit position is weighted by their binary value. Here it is 8421. So I will definitely ask you, maybe in exam, create a 5211 BCD code values, right? So then you must be able to do. So I will just help you how to do a 5211 code after we complete this. Yeah. So BCD is a weighted code with each bit assigned with weights 8, 4, 2 and 1. Okay, I think it is not there. Quickly, I will create a 5311 BCD code. Right. So the one that I showed you is an 8421 BCD code. It is 5311 code. Let us code 0 first. 0 in decimal can be coded as 0000. 1 can be coded as 0001. 2 can be coded as 00. 1 plus 1 will give me 2. So 1 and 1. 3 can be coded as 0, 1, 0, 0. And similarly, 4 can be coded as 0. My first priority will be highest value, 3, 0 and 1. 5 can be coded as 0, 1, 1, 1, right? So 3 plus 4 plus 5. Oh, I'm sorry. Yeah, you are right. Sir.
Sir, I'm having a doubt.
Yeah, please go ahead.
Sir, can we write 0110 for 4?
You cannot write 0110. No, for 4. Okay, 0110.
Yes, sir.
No, you cannot write, because the first priority among these both ones, you will give the highest priority to the most LSB value here. The most LS, this will get highest priority when compared to the next one. So we have written 0, 1, 0, 1. So 5, yeah, 5 will be coded as 1, 0, 0, 0. 6 will be coded as 1, 0, 0, because this will get a highest priority. This will be 1. 7 will be coded as 5, then 3, 1 and 1. Sorry, 0. Yeah, 1, 0, 1, 1. And 8 will be coded as 1, 1, 0, 0. 9 will be coded as 1, 1, 0, 1. And 10 will be coded as 8, 9, 10. All ones, 1, 1. Okay, now what are the invalid bits here? What are the invalid bits? Invalid bits are, I am just writing the invalid bits. Do we have, yeah, 1, 0, 0, 1, 0, 1. 1, 1, 0 is not there. So 0, 1, 1, 0 is an invalid bit in 5311. 0, 1, 1, 1 is an invalid bit in 5311. And then 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1. Yeah, is there any other bits we have? Well, 1, 0, 1, 0.
1, 0.
Yes, 0, 0, 1, 0, 1, 0, 1, 0. These are invalid bits. So how many we have covered? 10, 10 plus 4. Remaining, there are 2 more invalid bits. Let us find out. 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 we have written, 1, 1, 1 we have
1,
written.
0.
Yeah, 1, 1, 0. 1, 1, 0. One more. One more. 1000, 1001, 1, 0, 1, 0 we have written. 1, 1, 1, 0. Yeah, okay. Anybody? Yeah. Have you 1, 0, 1, 1? Okay. 1, 0, 1, 1. All right. We are having 1, 0, 1, 1 here. Okay, then yeah, this is how you find out. So these are the invalid codes. So, okay, now let us do how to convert a decimal number to a binary coded decimal number. Now, having known that these are the BCD equivalent decimal binary values, so the binary coded decimal values are, if you have a binary decimal value, then they can be coded directly as it is. 2 is represented as 0010. Please note that by default, if it is given as BCD, always presume, if it is BCD, why it's not writing? Yeah, if it is given as BCD, by default, it is 8421 code only. If nothing is given, always presume that it is 8421. Unless otherwise specified, unless otherwise if it is given as say 5311, then you have to follow that particular code. Okay, so 2 is represented as 0010, 4 as 0100, 6 as 0110, and 9 as 1001. Now, the immediate thing is, how do you perform addition of these BCD numbers? Obviously, when you add, say for example, two numbers, 8 and 2, 8 and 2 is 10, but this 10 is not a valid decimal number, right? Why 10 is not a valid decimal number? Because this is a combination of decimal number. This is not one single symbol. Okay, so now let us, when you add, then you will come across different problems. Now, what is the binary coded decimal of 25? 2 is represented as 0010. 5 is represented as 0101. 13, in 13, 1 is represented as 0001 and 3 is represented as 0011. When you add these two things, let us do it manually also. What is 25 plus 13? Sorry, 25 plus 13, it is 38. So 38 must be the answer. Let us add binary also. 1 plus 1, 0. 0 plus 1 is 0 with a carry 1, 0 and 1 here. And then 0 plus 1 is 1. 1 plus 0 is 1, 0, 0, 0, 0. So this is also equivalent to 38. So no issues at all. So you see here certain observations I have made. There is no carry. You are not getting any carry, right? There is no illegal code. What do you mean by illegal code? If you come across any of these particular codes in as a result of your addition or subtraction, then they are illegal codes. So which means that your sum is okay. Whatever the answer you got, your sum is okay. Now let us perform one more addition here. Now here comes the problem. I'm going to perform 679.6 and 536.8. I'm going to add these two things in BCD. I'm going to perform a BCD addition. Whenever I say BCD addition, by default it is 8421 BCD addition. 6 is represented as 0110, 7 is represented as 0111, 9 as 1001 and 6 as 0100. And now I have to perform similarly 536.8. 50101, 3 is 0011, 6 is 0110 and dot 8 is 1000. Now I am going to add. When I add, you see here, when you perform these two additions.
Excuse me, sir.
Yeah, please go ahead.
Sir, in the decimal, 6 is 0100. It is written here, but it is actually 0110.
Okay, yeah, you are right. Good, thanks for pointing out. So this is actually, this should be, as someone said, it is 0110. Yeah, this must be, I think I performed the calculation right. Yeah, 0 plus 0 was 0, 1 plus 0 was 1, 1 plus 0 is 1, and 0 plus 1 is 1. So 1110. Similarly, you add all these things. So 1 plus 0 is 1, 1, 1, 1, and 1. So 1 plus 1 is 0, carry 111. So 1, remainder 1. So 1 plus 1 is 0, carry 1. So it is 1010. Likewise 1011. Here the problem, if you look here, is you have come across certain invalid codes here. Out of this, what are the invalid codes? Obviously this is an invalid code. This is an invalid code. 1111 is an invalid code. This is also an invalid code. This is also an invalid code. Invalid codes means what? Invalid codes means we have come across an addition that has resulted beyond 9. It means that if you have come across 1110, what does it mean? It means that the sum has resulted in an answer of 14. What is 6 plus 8? 14 only, right? But we must have only 4. If you draw on a scale, if this is 9, and these are the invalid codes you have here, 0 to 9. After addition, you should not go beyond 9, in fact. After 9, we have, so 14 is where? 1, 2, 3, 14 is here. We should not go beyond 9. After 9, you have to come back and then you have to revisit this particular scale. So 9 must be added with these invalid 6 bits so that you come across a valid number. So what we do here is, whenever you come across an invalid code, you add plus 6 to it, because 6 bits are the invalid codes, right? So that is why we are adding it with 6. So all are illegal codes here. So add 6 to each of these numbers. And again, I have already said you the answer. Why 6? Why 6 is because you are having only 10 decimal values, and after that 6 bits are invalid bits. So we have to bring in this sum inside the valid BCD bits. So that is why we are adding it with 6. So when you add it with 6, what happens? Still there will be a problem. So when you add it with bits, so it is 0, 0, that is a carry, 1, and then 0, you are getting a carry again here, right? You are getting a carry here. So this carry will be added to this particular one, as simple as that. Okay, if you get a carry here, you add this with this one. Okay, so not right now. Let me complete this particular part. So you add it with a carry. Then you add this also. I mean, this is one additional step. Instead, what you could have done is you could have added this one along with this, and then you could have resulted. Otherwise, this is also fine. So it is 0, 1, 0, 0. I'm getting a carry. Here also you add 1 plus 0 is 1. 1 plus 1 is 0 with remainder 1. 1 plus 1 plus carry 1, 1. So you perform this. There is again a carry generated here. There is again a carry generated here. Again a carry generated here. Then as a next step, what you should do is add this carry with this particular one. So, right, so 0, 1, 0, 0, it is copied down, and then 0, 1, 0, 1, you add 1 to it, so it will be 0, 1, 1, 0. It is 0, 1, 1, 0. 0, 0, 0, you add 1, it will be 0, 0, 0, 1. So 0, 0, 0, 1, you add 1, 0, 0, 1, 0. Likewise, and then your carry bit, it is 0, 0, 0, 1. So what is the equivalent BCD sum? BCD's equivalent BCD sum here is 1216.4, meaning when you add 679.6 with 536.8, your sum is going to be 1216.4. Any doubt? Okay, so with this we will stop here. We will perform BCD subtraction in the next. Addition we have performed easily. It is straightforward. Now, when we perform subtraction, then you have to apply all the 9's complement rules, and at the same time, you must also apply all the BCD subtraction rules that you will come across the illegal codes here also. So all these things you need to keep in mind and then do the simplification. Any doubts here?